Hello, everyone, and welcome back to AI Tuesdays. My name is Erica, and I am the program manager at Microsoft React Stockholm. Today, we are going to continue with the fourth episode of the AI and machine learning track in the Championing Azure Collection series. This series is aimed to provide the necessary skills in Azure and is perfect for those early in their developer career. About a year ago at GamesTech Live, Microsoft Research announced Project Paidia, a research effort aimed at exploring new opportunities created with AI-based reinforcement learning in gaming. During this session today, you will be able to get started with reinforcement learning for gaming with the use of Azure Machine Learning. But before I can continue, I would just like to say a quick word about Microsoft's Code of Conduct. We all come from different backgrounds, but we are all here to learn. So please be aware of each other and be welcoming and respectful. Thank you. Our speaker today has collected some learning resources for you. So please take a screenshot and then go to this link. I will also drop them in the chat just in a minute. But now, let's move on to the reason we are here today, and let me introduce you to our speakers, Alan Smith and Eve Pardey. Alan, you probably are familiar with by now, as he has been a superstar in this series and has hosted many sessions already. For those who missed the previous episodes, Alan has been an MVP for over 10 years. He's a software engineer, evangelist, mentor, and has once been recognized as one of the top 10 developers in Sweden. Our other speaker today is Eve, and Eva has worked with Azure infrastructure, mobile, and web development. And today, she focuses on data science and machine learning. Eve is a familiar face at conferences, meetups, and other community events, sharing her passion for AI and how it can be used to improve life quality around the world. She's also mentoring and supporting people who would like to start in the field of data science and AI. So make sure you connect with her as well. The session is going to run about for 45 minutes with some question at the end. But I encourage you to ask your questions during the chat. They are waiting for it. I think I've spoken enough, so let's bring you guys now here to the stream. Hello.
Hi.
Hi, and welcome. Thank you so much for joining, Alan and Eve. It's such a pleasure to have you here today.
Yeah, it's good to be back.
Yeah, you're back, certainly back. Yeah, it's been, I think you've been like 5 times already. So, but thank you. It's really appreciated. And the audience love you. So, Eve, it's been your first time here, but I hope not the last. So yeah, I'm going to put myself to the background, but I will be here if I'm needed. So just shout out. I will be listening. Okay? Thank you. See you soon.
Great. So thank you for joining us again. And I mentioned in the YouTube chat, please feel free to interrupt us with questions. Eve's going to be monitoring the chat whilst I'm talking. I'm going to be monitoring the chat whilst Eve's talking. And in previous sessions, we've had a lot of great questions coming in, and it's always good to take additional discussions and so on. Okay, so I'm going to start with a quick intro. If you've not seen me present before, as Erica mentioned, I'm a developer, trainer, mentor, evangelist, or I describe myself as that. I work for a company called Active Solution, based in Stockholm, Sweden, and we have had a big focus previously on building .NET applications. We're now working a lot with Azure applications, and also exploring machine learning technologies on the Microsoft platform. So we do a lot with cognitive services, Azure ML, and these other technologies. And we're going to be looking at Azure ML a bit later on. Also, as an evangelist, I'm trying to get people at my company to program in Python. I think Eve will agree that it's really the programming language to be learning if you want to do stuff with machine learning. So I do a lot with the community. So we're kind of thinking of organising the AI Burst conference. Restrictions are lifting tomorrow in Sweden, so we can start planning for events. So hopefully we're going to get this conference running before the summer in Stockholm in Sweden. So I'm from the UK, but based in Stockholm in Sweden. This doesn't happen often that Sweden are at the top of the medals table in an Olympics. So it's great to see that from being in such a small country that seems to be punching above its weight in the Olympic Games. But what we're going to be looking at is video games and how artificial intelligence and machine learning can be used in video games. I've been doing this as a hobby project, basically working with using it as a way to learn about machine learning. It's a great way of being able to test algorithms and see how algorithms can adapt to different environments. And then I've been looking at more commercial applications, how big game developers are using it and using Azure Machine Learning to be able to basically build a better interactivity into the games, make the non-playable characters or NPCs actually behave like real players by using artificial intelligence and machine learning and learning how to play the game. So a bit about the machine learning we've been talking about in previous exercises. We talk about this supervised learning where we have data, we have answers, and we put this into a machine learning algorithm, and we train the machine learning algorithm, and we get some rules, or we get a trained model that's able to make predictions. With supervised learning, it makes this big assumption that we have the answers to the actual data. So previously I've been looking at, what's the price of an apartment? We need to start out with a big list of apartment prices in different regions and different areas and so on. Predicting images like cats and dogs, we have thousands of images of cats, thousands of images of dogs to train the model. And for music genres, we have, lots and lots of samples of various music genres that we can use to train a model. However, when we get on to reinforcement learning, we don't have the actual answers. We don't have, the way that an agent, what we call, or an artificial intelligence player should actually play the game. The agent has to figure this out for themselves. But with gaming, we get great simulations, and what we have is an environment. And there's various environments we can use. You could use the actual video screen of the game and the controls of the game to interact with the environment. With games like StarCraft, there's actually an API that you can use, so you can actually send and program against StarCraft and read and write data from the StarCraft API. So there's various ways of being able to interact with the game, but basically an environment is a game for our purposes. The environment will have some state. And this, for a game, it could be the actual screen of the game that is the state. It could be going into an API and reading information about where the other players are, where all of the objects are, and where the artifacts are in the game. But it's basically describing the actual state of the game at a single point in time. The agent is going to take an action. And this is basically, sending an input into the game to actually change or modify the environment. So it could be moving up, moving left, moving right. It could be shooting a laser, and various things like that. And we're going to get a reward out of the environment. If we basically make a move, it's going to put us in a better position within the game, and we're going to get a kind of a reward from that, which is going to be based on how well we're doing within the actual game. So for a driving game, it could be how far we've driven before we've crashed. For a Pac-Man game, it could be what is the actual score, or how many dots we've eaten. Just something that's going to increase as the agent gets better at existing in the environment or playing the actual game. So the agent is going to be the player that has an artificial intelligence algorithm. We feed the state into the agent. The agent is going to take an action that's going to modify the state, and we're going to get a reward, which is coming back and fed back into the agent. So this is kind of based on the infinite monkey theorem. If you believe this theorem, that if you put an infinite amount of monkeys in front of an infinite amount of typewriters, one of them will write the complete works of Shakespeare. The others will just write regular expressions. And if you basically add kind of evolution to that and genetic evolution, what you can do is you can basically take all of the monkeys that are typing Shakespeare, and you can select the ones that are basically getting the closest to Shakespeare, or producing, the best Shakespearean plays. And you can basically evolve those monkeys by using crossbreeding, and eventually, thousands or millions of years later, you'll get a monkey that can actually write the complete works of Shakespeare. I don't know if that would actually work successfully, but this is kind of the idea that we take when we think about genetic evolution. So basically, we're going to be looking at something called a genetic algorithm. We start out with an initial population. This is usually created randomly, and we'll have certain parameters and certain numbers in that initial population. It could be a neural network with various weights. It could be various parameters that are used for actually playing the game, or it could be a sequence of moves. If you think about StarCraft, when you start a new StarCraft game, the important thing is your build order. What do you start building first? So if you want to optimize the build order, the initial population could be 50 different agents with 50 different random build orders. What we're going to do is basically evaluate all 50 members of this individual population. And we need to be able to place some kind of score on those. So which build order is going to generate the most money, or the best resources, or the most diamonds or crystals per second, or whatever you mine in StarCraft. We need to be able to put a score on that. And then we can do our selection. We can choose the members of that population that have done best at the particular task. Then we do a couple of things that happen in natural evolution. We have crossover, where we basically take numbers or parameters from the best performing members of the population. We blend them together to be able to make a new population. Another thing that happens in natural evolution is mutation. So what we do is we randomly change maybe 1% of the actual parameters to basically interject a bit of randomness in there and hopefully optimize the way that the agents are going to evolve. And that goes around the first generation. And then we can run maybe 10, 50, 100 generations to see if we can get any improvement in that. And what we're looking for is an improvement in the score over time. So we want to see the score increasing over time. Okay, so various options to do this in various environments. I basically started out, one of the early ones I did, I was really, this was around about the time when it was the first Falcon Heavy launch. I watched this with my daughter. She's having trouble getting to sleep, and I brought her up and we watched the Falcon Heavy launch. It's fantastic to see those two rocket boosters landing simultaneously and successfully. So I decided to see if I can simulate this. Instead of using 2 rocket boosters, I'm using 25 rocket boosters. And what I'm doing is I'm putting in these random, what I call thrust vector tables. It sounds really cool, but it's just basically the engine thrust at a certain height that the rocket will make. So we feed these parameters into the initial population of 25 rockets, and then we put them in a simulator. I'm using the Unity gaming engine, and they're all going to crash, they're all going to blow up, and they're all going to explode. However, some of them are going to land with a slower velocity than others. So what we're going to do is to select the rockets with the lowest landing velocity, the ones that crash with the lowest velocity. And then we're going to perform our crossover. We're going to generate 25 new rockets, and we're going to basically randomly modify a small proportion of the values in these thrust vectors tables and go around the actual generations. So what we're measuring really is the actual speed and the altitude. We have these various parameters. As the rockets burn fuel, the actual mass of the rockets will decrease. So it needs to take that into account. So the calculations is rocket science to be able to perform these various calculations. So as the fuel decreases, the mass is going to change, and we have to think about how much thrust we're going to make. And then it's measuring the landing speed that's used to actually drive the algorithm. So landing rockets with a genetic algorithm, what could possibly go wrong, as they say on Top Gear? So I've got Unity here, and I've got my scene in Unity. I'll see if I can make it a bit bigger. If I run this simulation, what's going to happen is we're going to get 25 rockets, and you can see that they're all doing different things because the way that they use thrust at different altitude is different from all of these rockets. However, hopefully after a few iterations of the generation, they may start to land more successfully. It does look like they're crashing a bit. Some of them are crashing a bit slower than other ones. I have done this presentation, and we've sat here for a long time, and they just blow up the whole time. So it may not actually get any successful landings. We'll see how that goes. I'll just check the chat. So hello to London, and yeah, great to see you joining from London. Hi to Pakistan as well. Great to see other people joining, and it's great to have an international audience here. This doesn't seem to be too successful. What I think I'm going to do is just stop it and restart it again, because we use random numbers to initialize the populations. Giving them, a whole new series of random numbers may mean that it is going to be more successful. However, this does look a bit less successful than the previous one. So let's just give this a few generations just to see if it can land a rocket. And they just do seem to be blowing up. It works perfectly whenever I run this before the actual presentation, and then it just doesn't work during the presentation. So third time lucky. And they all blew up in the first generation. Let's see if there's any improvement. Okay, we'll give it another couple of generations, then I'll just move it onto a different screen, and we'll drop back to it if we do get any more success and they do start landing. I'll try and keep an eye on it. Just one more, because they did look like they were landing a bit slower in that generation. No, it's not working too well. So I'm just going to move this onto a different screen, and I'll leave it running. And we can drop back to the slides. I did say, what could possibly go wrong with this demo. I am basically driven by random numbers here. Okay. So basically the game state can be different dependent on the actual game. The first computer game that I ever played, it was back in the 70s, and it was a Lunar Lander game that you actually used a light pen to actually control the spaceship there. Now here the state could be the altitude, the horizontal speed, the vertical speed. It's a bit kind of the same scenario as I've got with my rockets. When you're working with these Atari games, there is also an Atari game simulator that you can run in an application called AIDream. And here it's the actual pixels on the screen. It's quite a low resolution screen. So you can actually take the values of all of the pixels and use that as the actual game state. For a driving game, it becomes more complex. You can see that there's a lot more information within this. Processing this type of image can be very challenging. So I've got solutions that can look at working with that. And what I was doing was I was generating a filter, a color filter on the screen. And what I was getting out is this, which is the actual optimal driving line. And by you doing a filter on this particular cyan color, you can actually get this as an actual output from that image filter. And that basically is providing a lot less signal to noise when you want to look at an AI that's going to drive a car around a track. So processing the actual image to be able to produce the game state can be useful as well. I also did experiment a bit with using the Azure Custom Vision service. So here I was looking at using the trained modeling custom vision to be able to identify other cars. And that would allow us to know the actual positions of those cars. Obviously, processing just the driver line doesn't tell me where the other cars are on the track. So it's just going to crash into other cars. It's not going to know what another car is. But giving it the position of the cars could help it to be able to take that into the equation there. Then the action, you can simulate a keyboard, you can simulate a joystick, and in a driving game, you can simulate the actual wheel. The reward is going to be, in this example of a driving game, how far you can actually drive in meters without coming off the track. So we calculate this by looking at the speed of the car and then doing a calculation over time. And as the speed increases, you can calculate the distance by speed over time. It's basic physics to be able to do that calculation there. For this, for the other ones, it's going to be like the speed at which you land. And for the Atari-based games, they're actually using the score that's coming out of the game. That's kind of unanimous in whether you're playing Space Invaders or Pac-Man or Donkey Kong. The actual score, the number of points that you get in the game, can be used as a way of being able to actually drive the actual reward. So the driving game example, I did actually experiment. I think this is Forza Apex, I think, one of the Forza games, which has quite advanced driving physics. And I used an actual control simulator to actually control the driving game. So I was taking in the state, and based on the actual state, I was modifying the input, the actual steering of the car. And I kept the car running at a constant speed so that it would just basically, keep driving. It wouldn't go too fast, wouldn't go too slow. And that was basically the way that I was running this. And the reward, as I mentioned, is how far it has driven down the track. I was really motivated by the AI devices we're starting to see coming out commercially. I was delivering a training course in Kista, which is just north of Stockholm, and they had an AI day, and this is one of the things that was basically going around. It's an AI sweeper, which could basically interact with people. If you stood in front of it, it would basically go around you and basically go around cleaning the streets in a certain area. This was a delivery truck that doesn't have a driver, and they were kind of prototyping this. This thing was driving at about 3 kilometers an hour, I think, really, really slowly, and able to, maneuver around the actual roads. And it was really interesting to see a completely autonomous vehicle in prototype form. If you do want to get into working with this programmatically, there is a simulator called Carla. I wouldn't recommend, from my experiments of working with a Forza game, that was really challenging, but Carla is really built as an open source simulator for autonomous driving research. So there is a Python API available for this, and you can get programmatic access to the actual state. You can get like LiDARs and depth sensors and image cameras and all kinds of information about the images. So you can basically build an experiment with your own driver AIs. So I'm going to run, it's really challenging to actually demo the Forza. So what I can show is basically the actual Forza in the experiment when I was actually running this. So starting off with the early generations, it doesn't really know how to drive. Then eventually, after a number of generations, it figures out that driving in a straight line is a good thing, because that increases the score. And then when we get a right turn in the road, the car turns left and goes out into the field. But eventually, it figures out that it can actually do better by following the actual line, and it is able to make that gentle right turn. You can see from the smoke coming from the tires, it does a full lock on the actual wheel, which isn't the most optimal way to drive a Lamborghini Aventador, but it does actually work. It does actually get it along the actual road. And what I'm showing is evolution over probably about 16 or 18 hours, and it was several days that I was running this simulation in total, and maybe going through about 50 generations. It took such a long time because each generation of, say, 50 cars, I had to basically play the game 50 times to advance through a generation. So it took a really long time to go through each generation. But eventually, it was getting further along the track and managing to navigate round gentle corners. However, when we got to the first really sharp corner, it had a real problem, and I never managed to get it to evolve to go around that sharp corner there. I think it's nearly towards the end, and in a couple of evolutions, we'll see, kind of as far as it was getting. Yeah, it would get to about here, and it would never make it round that sharp corner. So I kind of put that project on pause. I may return to it a bit later on when I do get more time. As I recommended, using the Carla simulation is much better. You can run like 50 agents at once and have them all exploring the environment. Another thing that I looked at, which was another hobby project, was the Global AI Bootcamp. We organized a racing game, and this is from the actual racing game that we were running. And the idea was that previously in the Global Azure Bootcamps, we've had this global racing game, which is built on Azure, and people around the world can basically drive a car around the lap and compete with each other. So what we decided to do for the Global AI Bootcamp is take that racing game and then give people the option. They can either basically drive around the track and attempt to set a time as a human, or they can train their own agent to be able to drive around the track and let it evolve, and let it start off with 0 driving skills and see how well it can actually evolve to drive around the track. This is a scenario of where we got stuck at a certain point. One of the things about these genetic algorithms is they can get stuck. And here, it was actually, it couldn't get much further than 733 meters, because at that point in the track, there was a really sharp corner. And it never figured out that, slowing down and turning the wheel would get it around that corner and get it a few more meters. So it did basically get stuck in that particular, what's known as a false minimum in machine learning. So looking at the self-learning, self-driving cars, I've been through already been through the demo of Forza. Let's see if I can get onto the next slide here. The global Azure Bootcamp racing game, this was a lot easier to interact with because we could actually get into the actual game, and we could actually read programmatically from the game these actual distances. So what I was doing was I was having distance sensors that was telling you how far away the barriers were. And these basically 5 parameters were fed into a neural network. And we evolved the neural network over time to be able to make additional modifications and see how the game evolves. So I've got a couple of videos from that. If I go back to the browser, this is basically false minimum. And previously, when I was working with this, I had sensors all the way around the car. So the car could basically detect backwards how far the track was away. And this is an example of something called a false minimum. And basically, the best car in the first generation just randomly turned around 180 degrees and started driving backwards. And that basically gave it the best score. And then all of the other generations evolved into thinking that driving backwards is the best way to be able to drive in the game. You can go a lot faster driving forwards than you can driving backwards, but these just kept evolving and kept driving backwards and just getting better and better at driving the car backwards around the track. And this is another example of something called a false minimum, where an AI algorithm can basically get stuck in a particular scenario. But it was very proficient at driving backwards. So then I removed the sensors behind the car, so the car couldn't actually see backwards. And then obviously then there'd be no way that a car that attempts to drive backwards could work, because it didn't have any sensor data from what was going on behind it. So the Racing Lab was very interesting in the Global AI Bootcamp, because we can see here that these are the actual top 10 positions coming out on the website. You can see that from Nigeria, the actual Nigerian AI was basically overall winner of this, and that basically beats the human player that was coming from Indonesia. So what I've done is I've basically used the Terminator skulls from the film Terminator as the actual AI players, and then I've used this is the Stig, the white Stig helmet from Top Gear for the actual human players. And within the the top 10, we've got kind of 3 AI players, with the AI player winning. And you can see that the human players are down here, and we do get a few AIs. There's Sweden Active Solution at my company that's come in with that particular score. This is kind of averaging the time across all 3 tracks. So the AI player had to basically compete on all three tracks here, and you can see that it's beating the human players on the first track, where it's obviously had the most evolution. I've still got my rockets on the other screen, and they are still crashing and burning. So maybe I'm not going to be able to show how those rockets are working. This is basically showing a bit more from the actual scores of this, the actual generation and the actual car from the generation. So you can see how many generations it's taken to evolve as it actually goes through the evolution process there. And that was again in the top 10, showing 3 out of the top 10 were basically these AI drivers. So getting into doing some programming yourself, there is an application called OpenAIDream, or it's a suite of software that allows Python developers to be able to create AIs in these simulated environments. So instead of working with a complex scenario like a driving game, we have these simple things like cart pole, where you've got to basically evolve an AI that's going to move this particular cart and keep the pole balanced for as long as possible. So here the state is the position of the cart and the angle of the pole. The inputs is move left and move right with a certain velocity, or I think it's a certain amount of force you can basically put onto the actual block at the bottom, the actual cart. And the reward is how many game steps, or the amount of time that you can keep the pole balanced for. So it's a really simple physical simulation that you can run using this. You've also got these walkers, so being able to evolve a quadruped to be able to learn how to walk and score it based on how far it can walk. That's another good example of using reinforcement learning. And then there's these various other games like Lunar Lander games, and they've also got all of the Atari games. This is the I can't remember the name. Is it the Atari 2600 that was in the early 80s? It was the game console that everybody wanted to have. And they've got all of the actual ROMs for that, so you can actually run all of these games. And they have actually been training AIs that are playing these games as good as humans will play this. Okay, so I'm going to hand over to Eve, and Eve's going to talk about how gaming companies are using this in production, and how they're working with using also the Azure Machine Learning technologies for this. My rockets are still crashing and burning. I haven't had any successful landings. This tends to happen when I'm doing a live presentation. However, 5 minutes later, I think when I run this again, it will probably succeed. I'm going to leave this running and just see if they have managed to successfully land by the end of the presentation. Okay, so Eve, are you able to take over?
Yes, thank you, Alan. It was a really amazing session as always, and I hope it will work by the end of the event. So please keep running your rocket science, and then we will check back on it in the end. So, welcome everyone. I am so happy that I can also be here to talk about something really cool today because Microsoft made an amazing history in machine learning and artificial intelligence, applying machine learning to improve many of their products and services, such as for the suggestions made in Office services. And I am really excited to share some insights today and offer a first glimpse into how Ninja Theory's game Bleeding Edge is allowing Microsoft research to drive exciting experimentation into artificial agents that learn to collaborate with humans with the use of reinforcement learning. I quickly want to say a few words about myself. I am Eve Pardy, a Microsoft AI MVP and a consultant at Avanade in the field of advanced analytics. And as Erica already told about me, I am really focusing on saving lives and improve the quality of life with the use of data and AI. I also focus on different other topics as well, where I try to make sure that people understand how intelligent applications affect our lives and how to use and control them. You can find many of my content and some videos on the internet if you look for that. I am the owner and the founder of AI 42, which is aiming to teach newcomers in the field of AI and data science because I really think it is important to make people understand the fundamentals of AI and data science so they can better, uh, um, apply these solutions in their own projects. I'm also a board member of global AI community, and if you would like to hear more about my project or would like to get some support in your own work, please don't hesitate to contact me. So we have seen many industries where reinforcement learning could be applied, like robotics, marketing, and I could go on. But the focus of this session today is game development, because gaming companies also have joined the personalization party. Really, why not tailor a video game experience like all the rules and the content, considering an individual player's skill level, the playing style, or the preferred gameplay? And so personalization of game experience is done through player modeling with the goal of increasing the enjoyment. So a player model in this case is an abstract description of a player based on their behavior in a game. And game components that can be adapted, they include space, mission, character, the music, the difficulty, and so on. And on the top of this, nowadays, it is also a consideration to improve the non human players of the games. Because think of a character or a bot in a game. It has to understand the state of the game, where are the players and objectives, and then based on this observation, it should make a decision. In reinforcement learning, decisions are driven by rewards, as we heard in Alan's session already. In a game, could it be a high score or a new level for reaching a specific goal? And the cool thing about a gaming situation is that the policy of the agent is trained under the pressure of the game. For example, it could learn what to do when it's being attacked or how to behave to reach a specific goal. And Microsoft proudly announced the preview of reinforcement learning on Azure Machine Learning. And this new reinforcement learning support provides the scalability while training to CPU or GPU virtual machines that also enable with machine learning compute clusters that can automatically provision, manage, and scale these virtual machines. You can also use different gaming environments, for example, OpenAIDream, and you can build your models with TensorFlow, PyTorch, and it supports on an X2. And the coolest thing, what I really like in this whole thing, is that you can also track your experiments and monitor the runs because Azure provides numerous AI solutions to build, run, and grow your games. So go on and accelerate your games with AI and machine learning to provide more realistic worlds and challenges for your players. I really can't wait to see what you come back with. So, non players' characters are the heart and soul of many video games. And new AI technology lets developers create characters that can organically and naturally able to respond to the player. And reinforcement learning models can be classified by the number of agents in the environment or, the players in a game that the algorithm teaches. The classic single agent reinforcement learning deals with having only one actor in the environment. So imagine yourself playing football alone without knowing the rules of how the game is played. You'll begin with randomly wandering the football field with no result at all, no rewards. And after some time, you would maybe start hitting the ball or kicking the ball, and then uh, not very often in the goal, making the reward very, very low. And then later, after several trials and errors, you would learn that you must hit the ball in the goal and try to achieve that consistently. Oh, sorry. Before I continue, for example, this agent here, this is inspired by Minecraft, of course, and the aim of this agent is to walk through solid tiles without stepping into the lava and reach the blue tile. And this agent also had many, many trials before he was able to go through on this difficult path. And it has been trained with different environments, so it learned how to generalize and adapt. So, in contrast with the single agent, the multi-agent reinforcement learning, you wouldn't be alone playing the game. So, assume that you are still playing football, but you have a single opponent and you both have your individual goalposts. So, your job now would be to ensure that you get as many goals or rewards as possible, irrespective of how your opponent behaves. However, your opponent is again in the same environment, maximizing the same objective, trying to learn the game. And in this case, if you hit the ball, he should try to defend it from going into his post. So notice the key difference here. Your goals are conflicting. And in a classical multi-agent environment, multiple agents would simultaneously act, affecting the learning process of each of the other agents. And the challenge here is that how can the agent behave optimally in order to how the player can take actions hitting as many goals as possible in the presence of an opponent who also shares the same objective. So this setting could transform the whole reinforcement learning into a game theoretical problem. Because, for example, think about the real world. Billions of people inhabit the planet, each with their own individual goals and action, but still capable of coming together through teams, organizations, and societies, and displays a collective intelligence. And this is a setting we call multi agent learning. Many individual agents must act independently, yet learn to interact and cooperate with other agents. This is an immensely difficult problem because with co adapting agents, the world is changing constantly. So the goal of Project Paidia team of Microsoft Research in collaboration with game developer Ninja Theory is to democratize state-of-the-art reinforcement learning techniques for any developer through Azure Machine Learning and to provide access to training infrastructure and easy integration tools. By this, make developers apply reinforcement learning while building exciting games for their players. And when it comes to video games, reinforcement learning agents have typically been trained to win against human opponents. Like this famous chess agent, have you heard about AlphaZero? Because AlphaZero is an AI program that learned the game of chess from scratch in 4 hours, playing against itself, and it was continuously able to defeat the strongest chess engine a few years ago. And the difference between AlphaZero and its competitors is that sorry, that its machine learning approach is given no human input apart from the basic rules of chess. What AlphaZero does is try to figure out what the optimal next set of move is. When humans can only think a few moves ahead, the AI can look a bit further using optimized search and planning methods. And so AlphaZero is said to be unbeatable by a human player, both in chess and StarCraft. This AI is built to beat human players. But what if we taught them to collaborate with human players instead? The game I want to show you is designed to rapidly test this collaboration between two players. And let me try and switch over to my browser. And I will need to look for, I don't know, why didn't I? No, that's another one. Reinforcement learning in gaming, idea, innovation. This project now has like 3 different setups, and I'm going to share these links with you after the session as well. But what I wanted to show you here, that we can start playing a game here. The idea is that we are logged in a spaceship in a room, and I will be the white agent, and the blue one is the one that is trained. Oh, you don't see my screen. Sorry about that. So there we go. So I'm going to be the white one, and the blue one is the trained agent. And what we need to do that one of us needs to press these buttons so these balls can fall into the holes. And then this guy should press this button and the door opens. So if I come here and press the button, the blue one opens, and then come for the yellow one opens. We have the ball, great. He is pressing the button so I can go out of here. But what if, and the cool thing that this agent is also trained for many different solutions, like many different environments, and he tries to adapt. So if I come here, I will take care of the switch. Thank you. Oh no, I changed my mind. I will press the buttons. No, okay, this button is fine with me. Or no, the switch instead. So see, he's trying to help me by adapting the scenario what I put him in, which is pretty cool. And we can just get out of here. Right. So what we needed to see and hear is that every time we try to train more than one agents, these agents has to be able to collaborate and help each other. So in this session, what we need to see is that there are these blue circles, and they are trying to find their space on these black landmarks without overlapping while spreading around. And for this, we can use OpenAIDream's particle environment within Azure Machine Learning. Just to make sure everything works, I decided that for this session, I'm going to show one of my previous demos because for a few days now, Microsoft is working on improving the Azure Machine Learning packages and the kernel for Python. So I just gonna go and look it like that. I switched over to my Azure portal. And to see this Azure portal, you will need an Azure subscription. Then you also need a resource group and a machine learning workspace with a computation cluster in the resource group. And I have already created a resource group here. But if you want, you can create a resource group as well by going to the resource groups and click create. And then all you have to specify is a name and the region for the resource group. And then you can also create a machine learning workspace by go to create new resource and say machine learning. And then you click create. Then you define a resource group and then specify a name. And also you can change the region to wherever you prefer. And then just create. But since the machine learning workspace is also created for us already, you can just go after it is deployed, you can click on it, and then launch the studio from here. When you arrive to the studio, this is the view you see. You can choose to work with notebooks and create your own code and build your own models and experiments. You can choose to work with automated machine learning, where you automatically train and tune your models, and you also get the best fitting model for your scenario. And then you can use the designer to use the drag and drop interface, where you can prepare your data and deploy your models as well. So now we need a compute target. So we go to the compute menu, and you can see I have already one that we are going to use today, but you can go and click create. And I would suggest to go with GPU for this scenario, and you can choose whatever size you prefer. And then just go next, and then you define a name. And then you click create. Now I won't create a new one because we have one already. So I just go back and go to our notebooks. So the notebook environment looks maybe familiar because if you have coded with Python, you might have used these IPython notebooks or the Azure notebooks as well. It also has a similar folder system, and you can also write your own code in here. So what I wanted to show you quickly is this files folder because it's really important. The files that are in this folder can be found on my GitHub account, and you can go to GitHub per Exaplione, and then there is the folder called reinforcement learning, and inside that, in the files menu, you can find all the Python files that you want to use for this one. All right, let's move back to our main folder, and I opened up the particle Python notebook, and then let's write some code. So the cool thing about these notebooks is that all the tools that we want to use are already installed for us. So you just maybe want to upgrade your environment, and then you're ready to use it. First, we return the SDK version for our Azure Machine Learning. This is quite handy in case you need to do some debugging. It is also a good idea to define which Azure tenant you want to use, so you can specify it with the use of the following code. And to find the tenant ID, you can just go back to the Azure portal and find it at the tenant properties. All right, now it is time to connect to the workspace. You can use configuration, or you can specify it by defining the name of the workspace, the subscription ID, and the name of the resource group. And if you want to figure out your subscription ID, you can also go and take a look at the subscriptions menu on the Azure portal where you can find details. If the connection was successful, then it will return the details of the workspace here. The next step is to create a new experiment, which will enable us to monitor the run. And as parameters, we pass the workspace that we just connected to, and we also specify the name of the experiment, which will be particle multi-agent.
The next step is to create a cluster where the training is going to run. So I specify the name here, that is CPU CLD3. And it is going to first look around in the system whether this cluster already generated. And if it is, then it is going to say, yes, I found find a compute target, so I'm going to use it. And if it is in a state that it is not available or stopped or whatever, that is going to return you that information as well. Otherwise, if the cluster is not generated yet, it is going to create a new one. For this, we have to specify also what size we want to have of this compute target, and we specify the number of nodes too. Here we specify that the 1 is the maximum number of nodes. The good thing about this cluster is that it will scale down when it is not used. And you are welcome to increase the nodes as well if you plan to run more than one experiment on this cluster. And when the cluster is ready to use, this code will return that either the cluster is created or that it has found an existing one and it is going to use it. So we are going to use a customized Docker image where all the necessary software and Python packages are installed. The configuration for the training run is defined with the environment class. And since we also want videos as a result about the different runs of the particles, we need to set the interpreter path too. For example, you set that it has to be this size, and other extensions information can be specified here too. For training, we are going to use the multi-agent deep deterministic policy gradient, or the MADDPG algorithm. And as the name suggests, it will be able to train many agents in the same time. If the training runs over 3 hours, it will automatically stop. And we have to initialize reinforcement learning estimator, also with different parameters. The entry script is going to be this Python file that we are working with right now. And the source directory with all the other Python files to use are found in the files folder. We also specify some parameters. For example, what scenario to use. We're going to use the simple spread scenario. And the final reward is set to minus 400. So while the reinforcement learning training is running, then when it is reaching the minus 400 reward, then it is going to stop automatically. We also define that the CPU cluster which is generated should be used, and that the environment is the environment that we have initialized in the previous step. Finally, we also want to see some run details about the experiment while it's running, and the button is available to navigate you to these run details thanks to this line of code. And if you go click on the run details here, then a new page is opening up like that. And go to child runs, click on this one. And if you go to outputs and logs, it will navigate you immediately to the driver log, where you can see each trials. What was the reward in the end of that specific trial? And if you scroll back, you can see the previous runs as well. And I also know that it's not easy to walk through and see each of the trials one by one. Instead, in the next the next part of the code, you can generate a tensor board, which provides you a link. If you follow that link, you can go and take a look at your tensor board, where you can see all the different run details about your experiment, all the information in live while the experiment is running. I think it's really useful because you can follow how did it change. And as you can see, it refreshes itself automatically. The evaluation of the training is really important, and it is possible to reach videos about the different iterations. And this code is going to generate these videos, and then this one is going to download them. and then displays it within the notebook. Look at this. So here you can see each of the runs, the whole video about the experiment, as the particles trying to find their path without colliding. You should run these codes, the TensorBoard and the video one, right after you start the training in order to see the videos and the TensorBoard correctly while the while the training is happening.
So with that, I want to say again, it is really, really nice to have Azure Machine Learning as a platform for us to build these reinforcement learning solutions, because you can monitor it inside the notebook and you can monitor it as in the details of the experiment and so on. You can find a few links on the page here which you can follow and find some more information. We will also share that with you in the chat. And remember to check out some of the Microsoft documentation to learn more about what you can do with with reinforcement learning in Azure Machine Learning, because there are really nice code samples for you. So I hope you enjoyed it today. I am very happy that I could be here. And Erica, thank you again for hosting, and Alan for the amazing pre-work.
Hello?
Yes. Yeah. How are the rockets, Alan?
Where is my picture? I'm purple. I don't know. I mean, okay. I don't know why. Can you hear me, guys?
Yes, we can hear you.
Okay, but do you see me?
No.
No. Okay. I have no idea why it's not working now.
Live
don't know.
event.
Yeah. This one has not happened to me before. It just shows me a big purple pink block. Anyhow, yes, thank you so much, guys, Eve and Alan, for being here today. I've just dropped in the as a last link to Eve's article that she's mentioned, and then all the other links up above that is to learning modules and to the GitHub that she mentioned throughout her session. Yes, Ellen, how are the rockets going? Are they?
Can you hear us, Alan? Because we can't hear you.
Oh, maybe now. Okay, we can hear you now, Alex?
You hear me now?
Yes,
Yes.
we can hear you now.
Yeah, they did land successfully. It always happens when it's a live show. Then the random numbers that are generated in the algorithms don't work. Maybe I need to fine tune their parameters a bit and set the landing speed a bit so they can land a bit harder. But yeah, they did. I think maybe you saw them in the actual stream, just evolving through the final few generations to get all of them landing there. Yeah, so that does seem to work. And I also in YouTube I actually shared a link to the Carla simulator that I mentioned at carla.org. So that will basically provide you can basically download it, and there's some tutorials and stuff to get you started.
Did you share it on this YouTube chat?
Yeah, I dropped the link in the chat. I'll drop it in again. It's just carla.org.
No, I don't think you are allowed. You can't send links. I don't think it's going to show up.
Yeah, that's the site anyway. I actually pasted the link in the YouTube chat, so hopefully it's appeared there. But there's plenty of tutorials on that that you can go through and just basically run with just build your own little simulators, and it's quite an advanced game world environment that you can work with. So they've got all kinds of stuff that we can generate in the simulator and different environments and things like that to be able to work if you're interested in self-driving cars.
Great, thank you. And yes, guys, ask your questions if you have anything to Alan or Eve. So yeah, because they are anxious to answer. I actually think there was one question from Lucifer here. Lucifer, I recognize that name. He's been with us, I think, the past few weeks. Is there going to be another boot camp like this in the future, especially for a game? I think he meant it when you were talking about the AI bootcamp, the global AI bootcamp.
Yeah. There is events from the global AI community. Eve's very active in this community as well. And they are planning different locations. So we can see there's some up and coming events. 12th of February, there's going to be some, and these are at different locations around the world. So maybe you can find sort of one that you can actually join and be able to be a part of there.
Yeah, we also would like to make a live event. I mean, face-to-face event soon.
Yeah, I miss pizza. I really want to get these actual global Azure boot camps and global AI boot camps running at physical locations again and get to meet people. And part of me for these events is the learning is good, but it's great to meet other developers as well and just talk about
Yeah.
stuff and technologies with people who've got a common interest.
Yeah,
Do you
keep an
have
eye
any
on this
active
page.
part? Sorry, Eve?
Just wanted to say, just keep an eye on this page because it keeps updating. There are a lot of places will pop up until March. So
Yeah, restrictions get lifted in Sweden tomorrow, so maybe we
also in Denmark.
we can think about doing something then. Yeah.
Maybe together with the reactor.
Maybe, yeah. You've got a great
Why
location
not?
there.
Yeah, it's in the middle of the city. But do you guys have any active part in the global bootcamp
Well,
organization?
I am supporting the organization a lot. We are trying to. So I am part of the board where we come up with ideas how to help the event organizers, what should be the content that we provide as a workshop that can be chosen to present at these events, and also some keynotes we are providing. We're helping with finding speakers and so on. So yes, so it's not
Yeah.
a big deal to make and organize an event because we are here to help you, of course, if you want to try yourself.
Yeah, I was actually in the team that did the original global Azure bootcamp way back in the day, together with I think there's about 6 of us involved in that original team. We were basically thinking that this would be a success if we got like 30 locations running boot camps on a single day, and that was just for the actual Azure community. And it's just crazy now. There's hundreds in the Azure bootcamp, and then there's a global AI bootcamp, there's a global integration bootcamp, and there's a global DevOps bootcamp. So it's great to see how popular this type of event has become around the world.
Yes, indeed. And as you guys mentioned, now that the restrictions lift, maybe we can even get together. And
Sounds good.
Yeah, hopefully, fingers crossed for that. Meanwhile, we wait for some people to catch up on the session. I'm going to just quickly come to this. So we have 2 sessions left from the beginner content of this part of the series of the season 1. Next week we are going to have Azure Custom Vision, and then we're going to have Azure Machine Learning. If you are also following the cloud native and the DevOps track, we have tomorrow containers and Docker, and then Azure Container Apps and Kubernetes Service for the next 3 weeks. And on DevOps, we have infrastructure as code tomorrow, and then we're going to be testing and monitoring. And then in March, we are going to be continuing this series with intermediate content. So yeah, just make sure you RSVP to your regional meetup, and then we see you here. So no questions. No questions. You guys were really good. No questions. Then yeah, any last words, Alan or Eve?
Yeah, thanks for putting this session together. It's been great to run these in the evenings, and looking forward also to the intermediate sessions as well. And
Yes.
I'll be here next week looking at the custom vision. So there's going to be plenty of images of cats and dogs when we're running that one. It's going to be good fun.
Can we get some techno again? A bit of
yeah, I might do music classification. Yeah, that does work in the custom vision service. I'm just experimenting with that, so maybe there can be some music coming. The music is actually from Robert Fulkinson, who's doing the presentation on Azure Machine Learning. So he very graciously let us use that music, because music's always got copyright on it, so it's great to get some good music that we can actually use, where the composer and the artist actually allows us to use that.
Yes, that is really great. I've had events where it got shut down because of copyright issues, believe me. It's not so much fun when the live stream just stops. But yes, then I think we're going to wrap this up now. And once again, thank you. Thank you so much that you've been here today. It's so annoying that my picture is not working. I don't know why. But I am here. I'm waving at you. So yeah, thank you so much. And guys, I will see you next week. Make sure you sign up and come next week. Thank you. Bye.
Thank you.
Thanks.